Hi class, I wanted to cover the next section 4.9, antiderivatives. So a function big F is called an antiderivative of little f on an interval I if the derivative of big F equals little f for all x in I. So what we're saying right here is big F is called an antiderivative if the derivative of big F is equal to little f of x. So what we're trying to do here, we'd be given a function f of x, which is the derivative of some function, and we're trying to figure out what function it's the derivative of. That's what we call the antiderivative. So if big F is an antiderivative of little f on an interval I, then the most general antiderivative of little f on I is big F of x plus c, where c is any arbitrary constant. We have to put the plus c because when you think about it, if you're taking a derivative of a function, if there's a constant is one of the terms of the function, when you differentiate it, it becomes zero. The constant becomes zero. So when we're given a function that's a derivative of another function, if the original function had a constant, you wouldn't see it in its derivative, or you would not know it from its derivative normally. So we have to go plus c, and c represents any constant. So that's what we're talking about, and that's what I just mentioned right here. Like if you have a function cosine x plus 3, and you take its derivative, that would just be negative sine x. We wouldn't know, the derivative of the constant would be 0. So when we anti-differentiate, so we'd be given this. We wouldn't know what this is. We'd be given this. We anti-differentiate, so the antiderivative of a negative sine x is cosine x, and then we have to go plus c. Now sometimes we're given some extra information so we can determine what c is, but most of the time we're not, and so we just go plus c. Okay, so I'm going to do a lot of examples in this section. So we want to find the most general antiderivative of the function, and here's the function. So we want to find the big f of x such that the derivative of big f of x is this little f of x. So we're given we're given a derivative, and we want to anti-differentiate to find the function that it's the derivative of. So anti-differentiating is like the inverse of differentiating, or we're undifferentiating or anti-differentiating. So the way you do this is it's the opposite of differentiation. You add 1 to the exponent and divide by the new exponent. So you add 1 to 9 and you divide by 9 plus 1. You add 1 to 6 and divide by 6 plus 1. You add 1 to 3 and divide by 3 plus 1, and then you have to go plus c. And you'll miss problems if you don't go plus c. So I just simplified that here, and that is my antiderivative. And then I simplified it some more right here. Now, you could always check an antiderivative by differentiation. So if this is the antiderivative of the function that we had, then that means that when we differentiate this function, we should get the little f of x that we were given. So, is the derivative of this function the little f of x? If so, then it checks. So I just differentiate, so I bring down the 10 and I subtract 1 from the exponent. I bring down the 7, I subtract 1 from the exponent. I bring down the 4 and multiply it times the 3 and subtract 1 from the exponent, and the derivative of the constant is 0. I simplify that and I get this function, which was the function that was given originally. So that's anti-differentiation. So what we did here for this particular antiderivative is we really did the power rule in reverse. So instead of bringing down the exponent and multiplying by and subtracting 1 from the exponent like we do with differentiation, we add 1 to the exponent and divide by the new exponent. Okay, here's another example. So I want to find the most general antiderivative of this function. Now I need to rewrite it with its fractional exponents. and then I need to add 1 to the exponent and divide by the new exponent. So I add 1 to 3/4, add 1 to 4/3, divide by those new exponents, and I get this. And then, of course, I want to fix that, I want to, dividing by a fraction is multiplying times the reciprocal. And then is the derivative, so this is my answer, but I can check it. Is the derivative of this equal to little f of x? So I differentiate just to check. And so I bring down, let's see, that is 7/4. So I bring down to 7/4, and 7/4 minus 4/4 is 3/4. I bring down the 7/3, and 7/3 minus 3/3 is 4/3. And then I clean that up, and that is the function that was given to me to start with. Okay, here's another example. We want to find the most general antiderivative of the function. So here's the function. When I have a radical, I want to write it with its fractional exponent. And then I add 1 to the exponent, divide by the new exponent. Now, the antiderivative of cosine x, or 6 cosine x, you kind of have to think backwards. What function has a derivative of 6 cosine x? That would be 6 sine x, and then we go plus c. So when you're doing this, don't differentiate, you're anti-differentiating. And then I just need to simplify this, and then I change this to multiplying by the reciprocal, and this is my answer. Now I check it, so I'll bring down the 3/2 and subtract 1 from the exponent. The derivative of 6 sine x is 6 cosine x, and the derivative of the constant is 0. So I get back to 2x to the 1/2 plus 6 cosine x, and that was what I started with originally. So this is actually a table. These are the functions, and this is the antiderivative. And then here's another column. This is the function. This is the antiderivative. So some of it, if you've got a constant times a function, you just go the constant times the antiderivative. If you've got a sum, you can just break it down into the sum when you find the antiderivatives. Now this is what we were using a minute ago, which is like the power rule in reverse. As long as n is not equal to 1 or -1, you add 1 to the exponent and divide by the new exponent. If n is -1, then this is 1 over x, and the antiderivative of 1 over x is the natural log, but you have to go absolute value of x so that the function's defined, because x has to be positive in order to take the log of the number. And the antiderivative of e to the x is e to the x. Now this is where you have to be a little bit careful. The antiderivative of cosine x is sine x, and the antiderivative of sine x is negative cosine x. And that may seem backwards, and it is. But you think about this function. If this is the antiderivative, really this is its derivative. So the derivative of sine x is cosine x. The derivative of minus cosine x would be minus and minus sine x. So just try to keep that straight. If you've got the secant squared x function, well, then its antiderivative is tangent x, because the derivative of tangent x is secant squared x. If you've got secant x tan x, then its antiderivative is secant x, because the derivative of secant x is secant x tan x. And then we've got our inverse, and I don't know why they don't have cos inverse x here, because you certainly could, but if you've got 1 over the square root of 1 minus x squared, its antiderivative is sine inverse x, and if you've got 1 over 1 plus x squared, its antiderivative is tan inverse x. And we don't use these hyperbolic functions. We don't teach that in this class. So let's see where we are now. Probably another example. So sometimes we can solve for c, but we have to be given some information to do that. So we want to find the antiderivative f of x. We're given little f of x, and we're given this extra piece of information that big f of 1 is equal to 0. So that means the antiderivative evaluated at 1 is 0. So the first thing we do is we anti-differentiate, and I just wrote it in this form. Now, when it's a constant, then that's really like x to the 0. So I'm just rewriting that right here because x to the 0 is 1. So we just use the power rule in reverse. We add 1 to the exponent, divide by the new exponent. So the antiderivative of 4 is 4x minus 3. This 1 over 1 plus x squared is a derivative of tan inverse x. So its antiderivative of this is tan inverse x, and then we have to go plus c. So here's my antiderivative. Now I know that this function, the antiderivative evaluated at 1 is 0. So I can use that to solve for c. So f of 1 would be 4 times 1 minus 3 times tan inverse of 1 plus c, and that's 0. Now that's 4. Tan inverse of 1 is the angle pi over 4 because the tangent of pi over 4 is 1. So this means what angle has the tangent of pi over 1, and that's pi over 4. So I have 4 minus 3 times pi over 4 plus c equals 0. Or in other words, c is equal to 3 pi over 4 minus 4. That's my answer. Now you can check it, or well, I didn't actually check it here, but my final answer is the antiderivative, and then I just wrote in the constant right here. That's my final answer. Here's another example. So in this example, we're given the second derivative, so we're going to anti-differentiate twice to get back to the little f of x. So instead of saying big f of x, we're using, well, because big f of x is just the first derivative of f of x, so we're given the second derivative. So we anti-differentiate f double prime to get f prime, or we anti-differentiate the second derivative to get the first derivative. So the antiderivative of 2 is 2x. The antiderivative of x cubed is x to the 4th over 4. The antiderivative of x to the 6th is x to the 7th over 7, and then we add our constant. Now, then I anti-differentiate once more to get what I'm looking for, my f of x. So I add 1 to the exponent, divide by the new exponent. I add 1 to the exponent, divide by the new exponent. I add 1 to the exponent, divide by the new exponent. The c, the antiderivative of c would be cx. And then we have another constant, so we have to go plus d. I just cleaned that up a little bit, and then this is what f of x would be, the original function. Now, I don't know, unless I'm given some more information, what c and d are. Okay. Okay, here's another example, and in this example, I'm given the second derivative, and I'm given some information so I can solve for c and d. So I first start with my second derivative, and I'm going to rewrite it. The square root of t would be t to the negative 1/2. And then to find the first derivative, I add 1 to the exponent, divide by the new exponent, and I have to go plus c. So I get 6t to the 1/2 plus c. Now I can solve for c here because I was given that f prime at 4 equals 7. So I evaluate f prime at 4, so I substitute in a 4 for t, and that should give me 7. So 4 to the 1/2 is just 2. So I've got 12 plus c equals 7. So then c is going to be equal to negative 5. And this is the first derivative. Now I anti-differentiate again to find f of t. So I add 1 to the exponent and divide by the new exponent. So the antiderivative of minus 5 is minus 5t, and then I go plus d, another constant. But I was given that I simplified this first, but I was given that f of 4 equals 20, so I can solve for d. If I substitute in 20, 4 right here and 20 over here, then 4 to the 3/2 is the square root of 4 cubed. So that's square root of 4 is 2, 2 cubed is 8. So I have 4 times 8 minus 20 plus d equal 20. or 32 minus 20 plus d equal 20. So I'll get 12 plus d equal 20, or d equals 8. And so this is f of t, and don't have a c and d because I was able to solve for those. Okay, class, let's talk about motion problems. Anti-differentiation is particularly useful in analyzing the motion of an object moving in a straight line. Recall that if the object has position function s equal f of t, then the velocity function is v of t equals s prime t. This means that the position function is an antiderivative of the velocity function. Likewise, the acceleration function is a sub t equals v prime t. So the velocity function is an antiderivative of the acceleration. If the acceleration and the initial values s of 0 and v of 0 are known, then the position function can be found by anti-differentiating twice. Now, an object near the surface of the Earth is subject to a gravitational force that produces a downward acceleration denoted by g. For motion close to the ground, we may assume that g is constant, and its value is about 9.8 meters per second squared. That's if you're given all of your units in meters per second, or 32 feet per second squared if you're given your units in feet. So we'll use that to do the next problem. So these values that they give right here, these are the accelerations. So when you're talking about on Earth and you're talking about something falling, or being thrown up, or it's moving, the acceleration is going to be the gravity, and it's going to be negative because the gravity is forcing the object down. So like if an object goes up, it doesn't keep going up. It goes up so far, and then it's forced down because of the gravity, which is the acceleration. So let's use that to do a problem. So a stone was dropped off a cliff and hit the ground with a speed of 120 feet per second. What is the height of the cliff? Okay, so it's thrown off the cliff, and we want to know what the height of that cliff is. Now, it's given a speed that it hit the ground, and if it's falling, that is the velocity is going to be negative, and the velocity would be negative 120 feet per second. Now, the acceleration is just due to gravity, so it's negative 32. Now, we start with the negative 32. That's the acceleration, and we start with the acceleration and we anti-differentiate. So it'll be negative 32t plus a constant, and that constant is the initial velocity. Now, sometimes you might be given the initial velocity, but in this case, the stone was just dropped. So it wasn't thrown downward. If it was thrown downward, there would be some value for the initial velocity, but it was just dropped. So the V naught is 0. There was no velocity, or it was just 0 initially. Now, that gives me that the velocity function is negative 32t because the V naught was 0. Now I'm going to anti-differentiate that, and that's going to give me s of t. So I add 1 to the exponent, and I divide by the new exponent, and I have a constant. And that constant is the initial position, s naught. But in this case, it's actually the height of the cliff. So that's really what we're looking for. So my s of t is negative 16t squared plus s naught. I need to find s naught. Well, there's one piece of information we haven't used, and that's that it hits the ground with the velocity of negative 120 feet per second. So I can solve this because I know that when it hits the ground, the position function is going to be 0. So we know that v of t equals negative 120 when the stone hits the ground. Now, what I can do is use that to find t. So I've got negative 32t, that's the velocity, and I know that when it hits the ground, it's negative 120, so I can solve for t. I solve for t, and it's 3.75 seconds. Now, I also know that when it hits the ground, the position is 0. And I know that this is the position function. I just don't know what S naught is. But I know that S of 3.75 is 0. So I put 3.75 into what I have for my position function, and I know that's 0. And then all I have to do is solve for S naught. This gives me a negative 25, or negative 225 plus S naught equals 0. So S naught equals 225, and that's the height of the cliff. Okay, so that concludes today's lesson on 4.9. So hopefully you can do your homework on 4.9 now. And please let me know if you have any questions. And don't get behind on your homework. I'll talk to you later. Thank you.